Okay, we're back, and I'm going to wrap up chapter one with a dynamic description of density and derived units. All right, so you probably remember density. Density is basically how much matter you have for how much space you take up. And when you're dealing with density, just know that it is going to be D equals M over V. And also, sometimes we use density as a conversion factor. So like 2.65 grams is equal to 1 cubic centimeter. So cubic centimeter is a way we express volume. Remember, volume is equal to length times width times height. And all of these are actually derived units. You see, it takes more than one unit to describe it. That's a derived unit. So if I'm just measuring the length of this stylus, I can use centimeters or meters or whatever. But if I'm trying to measure my speed, I have to use miles per hour, meters per second, something along those lines. It takes 2 units to describe those things. All right, so anyways, which of these observations is qualitative and which are quantitative? So qualitative would be something like it's blue-green. That would be an intensive property. And a quantitative would be, its mass is 2.5. Which of these observations are extensive and intensive? Well, the color is always intensive, and extensive would be your mass. Now the question is what's density? Is density intensive or extensive? Does density of an object actually change? Like, let's say I chop that rock in half, would the density be cut in half? Well, no, because if you chop the rock in half, the mass will go down, but also the volume will go down. So density is actually an intensive physical property. So a lot of kids miss that. Now, when you solve this, you just have to plug and chug into that lovely formula there. So what is the volume? So we know that the mass is 2.5, and we know we're going to be solving for V, and we know the density is 2.65. So if you just solve for V, and I always have my trusty calculator in chem class, so you need a scientific calculator. You knew that, right? So you get 0.94, and the units would be grams per, or for this one would be cubic centimeters, sorry. Now notice that I rounded to 2 significant figures because I'm limited to that number of significant figures when I do my calculations. You limit around to at least one. Sig fig discussion is coming up soon, so keep that in mind. Okay, now dimensional analysis. So this is just a little bit more practice. I want to kind of talk about dimensional analysis when it's not metric. So when it's metric, you're going to go back and you're going to use this chart, and you can just use these values. If you memorize this chart, if you memorize what each one is, if you know that there's 100 centimeters in a meter, it's super easy. Everything's base 10. The more you use it, the better it gets. But for this type of dimensional analysis, this one you have to use specific random conversion factors that I'm not going to make you memorize. So let me show you an example of this, and we'll talk about how to do this problem like this, and I'll show you the different types of this. So 1.3 times 10 to the 5th centimeters, and what we're going to do is we're going to go and figure out how many miles we have there. Now, again, you're going to notice that in chemistry class, everything's going to be in scientific notation. In my calculator, I'm going to use the EE button. It'd be like right above the 7-second comma. Or in this calculator, I'm going to use the EXP button when I'm writing stuff in my calculator. Or, you can actually convert it to a real number, like just not a real number, but a normal number if you really wanted to. But whatever's out in front is significant. That's going to be important when we do our final calculations. So anyways, let me get this to something that I know. I don't know how many centimeters are in a mile, but I do know how many centimeters are in an inch. And I would have to look this up or just memorize it, but it's 2.54 centimeters in 1 inch. Okay, now when I do dimensional analysis, it's very important, right? These have to be set up so that they cancel out. Very important. And the units will always be, matched up that way. And then this is the conversion factor. You have to usually look that up if you don't know it, or just memorize it. Now, I'm not going to make you memorize US customary ones with metric. You don't have to know that kind of stuff on the AP exam. Just know metric. That's all you have to know from me. But if I do give you this problem, I would have to give you the conversion factors. You'd have to set it up. Okay, then I know that there's 12 inches in 1 foot, right? And then inches cancel out. So I can set that up. And then I know that there's how many feet in a mile? So a lot of people know this random fact. It's 5,280 feet is equal to 1 mile. And then those get canceled out. And so to solve this out, what I would actually do is I would type in 1.3, times 10 to the fifth, and I would hit divided by 2.54, and I hit equals divided by 12, hit equals divided by 5,280, and I get 0.8. You get this number, 0.80778. And because these are all conversion factors, there's unlimited numbers of sig figs in conversion factors. They're exact numbers, all right? This is the only measurement, and since this has two sig figs, I would round this to 0.81 miles is my final answer. Box it in, boom, I get points. Okay, now, I haven't talked about sig figs yet. That's just the general format is whatever you're given in a problem, that's what you round for in dimensional analysis. So that's an important part of Chem. Okay, now you're going to see this part, and this part is tricky. So sometimes you're going to be given two things like this, and how do you convert these? So what you do, oh shoot, I have to get my pen ready. You're going to go 10 kilometers per minute, 1 minute. Do you see how that's what they give you? And then we're going to set up our bridge, and I know that there's 1.6 kilometers in 1 mile. Now you might not know that, but you could look it up, okay? I think it's like 1.609 or something like that, but doesn't really matter, okay? Now kilometers cancels, and you could Google, if you don't have a conversion factor this year, just Google it and find it, all right? And then we know that in, there's what, 60 minutes in 1 hour, right? So minutes would cancel out. And then do you see I have miles and hours left after I cancel everything out? So now to do the math, what I would do is with my trusty calculator, wait, get there. I would do 10 times 60 and hit equals. Now, technically, what you're supposed to do is whatever's up top, right, 600, divided by whatever's on the bottom, the product on the bottom, divided by 1.6, gives me 375 miles per hour. That is dimensional analysis. That's a major way of solving for it. Now, does everyone see that this isn't rounded in sig figs, and this is the only measurement? Remember, conversion factors, there's unlimited numbers of sig figs in there. So technically, there's only one sig fig, and this is probably on me. I probably should have given more to this problem, but this would actually, one sig fig for this would actually be 400. Or I could write 4 times 10 to the second miles per hour. I like that a lot, okay? And that shows you the right number of significant figures. So keep that in mind. All right, here we go. One more dimensional analysis. How many cubic feet are in 3.5 times 10 to the fifth cubic centimeters? Oh boy. Okay, so here's the rule with cubes and squares and all that other stuff is whatever you do to the, like the unit, you have to do the conversion factor. So for example, if the unit is cubed, you have to cube the conversion factor. Let me show you how to do this type of problem. So you're going to write 3.5 times 10 to the fifth centimeters cubed, and I'm going to get it into feet cubed. And here's the thing. I know that there's 2.54 centimeters in 1 inch. Okay, but how many cube centimeters are there? Well, there's this cubed in this cube. Now, 1 cubed is still 1, but basically what I'm saying is since I cubed the units, I have to cube the conversion factor, 2.54. Remember, that's how many centimeters are an inch. Okay, so then we'll keep going. And then there are what? 12 inches in 1 foot, right? But in a cubic foot, there's 12 cubed in inches cubed in 1 foot cubed. So really what I have to do, the math behind this one is 3.5 times 10 to the fifth, divided by 2.54, 12 cubic feet. All that work for 12. All right. So anyways, I'll edit that out and clean that up. You won't even know that magic happened. Except I just told you. Dang it. Okay. Now, let's talk about this whole thing because I've been messing with sig figs this whole time, and the number one thing kids don't pick up from summer work is sig figs. And unless you've experienced chemistry for a while, you don't get sig figs. So sig figs represent how accurate or precise you are in a measurement. Actually, not precision, but just accurate. So there are like good tools to measure with, and there are bad tools to measure with. And our numbers should represent how accurate we were in the lab. Okay, so when you measure something, there's always a little bit of bias that goes along with it. And so what some people see as, we call that bias uncertainty, right? That we're not quite certain of it. So for example, if I have the world's best measuring instrument and I measure this stylus, we're back to the stylus again, and I get that it is exactly, according to my measurement, that it's like 10.0050 centimeters long. Like we know pretty certain because there's a ton of digits, that's pretty close to that. Now, if I get a really bad ruler and it's like it's got missing parts to it, and I'm like, it's about 9 centimeters. See, this is not as accurate a measurement because I don't have as many digits. And that's the thing about significant figures is our numbers should represent how good we were in lab, and we're going to eventually get in lab, so that's an important part. Okay, now accuracy is how close to the mark you are. So accuracy in chemistry would be hitting the bullseye. Okay, so in this picture, this guy, you can barely see it because I'm kind of in the way, but this guy hits the bullseye, so he is accurate. Every once in a while, you can get lucky in lab and just hit the right answer, and you're just like, yay, we won. Okay, precision though is doing it over and over again. So this person is accurate because they were pretty close to the center, but they're all over the place. So this is why we do multiple trials sometimes. Now this person is precise because they're all grouped together. So precision deals with like sets of data. Accuracy is actually hitting the mark. Now, another type of measurement, or not measurement, but something to consider is exact numbers versus inexact numbers. So an exact number is like a definition. Okay, so for example, an exact number would be, 12 inches is 1 foot. Like that's a definition, right? Like by very definition, 12 inches is 1 foot. So there's no sig figs in an exact number. It's just there's unlimited. Okay, another exact number. There is one person in this room right now. Like when you count stuff, there's no uncertainty in that. I'm the only one here, right? You can be certain of that. Now, inexact numbers would be things that when you measured something, if I were to measure this tool or this stylus and I was just a little bit off, that would be that. And so inexact numbers or measurements require significant figures. And since we do a lot of measurements in a lot of labs in chemistry, you must record significant figures. All right, so when you're doing sig figs, here's the rule. So anything that's not zero is significant. And significant just means that it's a valid, important part of a measurement. So for example, if you get 20, let's do this. If you get 22.4 liters, that would have 1, 2, 3 significant figures, and you're done there. Whereas if I have 22, that's 2 sig figs. If I have 2, 2, 2, 2, 2, they're all significant. Anything that's not zero is significant. It's important. So if you were to count how many sig figs, which you normally do, you just count how many things aren't zero. So the question is when is zero significant? Well, leading zeros are not significant. So in this case right here, this has 2 significant figures because really I could just write this in scientific notation, couldn't I? And if you can write it in scientific notation, that means that it's not really that important. It's just representing the size of the measurement, not necessarily the accuracy. Now, captive zeros, these would be sandwich zeros, are always significant. So in this case, anything in between is significant. Okay? And so we call this sandwich rule because it's a sandwich between 2 non-zero digits. And then finally, trailing zeros are significant if there's a decimal, but if there's no decimal, there's not. So for example, in this case, at the bottom, there's 1 significant figure because there's no decimals, where anything after the decimal is significant. So for example, if I have 100, that's 1 sig fig. But if I have 100 point, that's 3 sig figs. If I have more than that, they're all significant. Okay, so another way to look at this is when zero's not significant. Okay, these 2 things, when it's like that, no decimal, and when they're before a number, they're not significant. Every other time they are. Okay, so that being said, let's get on to rules with adding and subtracting. So when you add and subtract, you are limited to the least number of decimal places. So for example, if I add 1.0 plus 1.000 plus 0.1, we'll just do that way. Then I have to add to my least number of decimal places. So this would be 3.1 because the farthest it gets is the least amount of decimal places to the 10th. Now, when you multiply and divide, the least number, it's the least number of significant figures. So, for example, if I do 1.0 times 3.99999, I'm going to get 3.999 repeating, right? And I can only keep 2 sig figs because I'm limited by how many I have. So I would have 4.0 as my answer. And we only round for things that are inexact or measurements, but that's pretty much all of our stuff in chemistry is going to be like that. So yeah, that's significant figures. Now, sometimes you're going to get something like this. So in this rule, this is a multiplication rule. You see that when I multiply these two together, I get a big number. I get 3.444, but I can only keep one significant figure because that's all we have here. So I would round it to 3. Now, if this was a 5, I would round it to 4. Okay. And then if I'm doing this one, do you see I only have 3 significant figures? So this is my 3 significant figures that I round. Remember, zeros before are not significant. When you have multiple operations, you kind of have to keep track of it. Do you see how if I did this operation, I'd have 20.5 as my answer there? And do you see how that has 3 significant figures? And that if I divide that, I'm dividing it by 2 significant figures. So my final answer should be 2 significant figures. So it should be 6.8 is my final answer. Box it in because that's what you do. Okay, so that being said, that is pretty much it for the chapter 1. There's a lot there, and what I plan on doing is some work where we, practice a little bit in class. But that is chapter 1 at a glance. Bye all. Pause this up. Just going to stop it.